Here we're going to talk about the constructive interference of X-rays emitted from a crystal. Specifically, when I take X-rays of a fixed wavelength, shine them at a crystal, and look at the light scattered from the crystal, I'll find that only certain angles will exhibit constructive interference. To see this, let's just look at this simple model of a crystal. This is just two planes. The indices for these planes are H, K, and L. We know that the planes are separated by some distance, and that distance is given by this formula. How do I know whether there's constructive or destructive interference? Well, let's just show some rays hitting this crystal. So here's one ray here, and here's another ray. This one's being scattered from the second plane, and this one's being scattered from the first plane. In this experiment, what I envision is I have a plane wave, which consists of many rays, coming in at an angle theta with respect to the planes. And I ask, will the scattered light from each of these planes constructively or destructively interfere? That's the same as asking, is the path length difference for the two rays equal to an integral number of wavelengths? So to assess the path length difference, let's just put some triangles in here to allow us to estimate the path length difference between the two rays. So the first triangle here describes the difference in length of this ray and this ray before it hits each of the respective planes. The path length difference is just BC here. In addition to the path length difference before it hits the respective planes, we also have a path length difference after it leaves the respective planes, and that path length difference is just B prime C. So what are these lengths? Well, this one's trivial, right? Since B prime C is the hypotenuse, and since this angle is 2 theta, then BC equals B prime C times the cosine of 2 theta. This one here is pretty easy too, because it's just, if you look at this right triangle, and this is theta here, you see that the B prime C has to equal the spacing between the planes divided by sine theta. The criteria for there to be constructive interference on this ray is that the total path length difference between these two rays has to equal an integral number of wavelengths. So we can write that total path length difference as B prime C minus BC, and that has to equal an integral number of the wavelengths of light that I'm using, specifically the wavelength of X-ray I'm using. Well, BC, as I've said here, is just B prime C cosine 2 theta. And I factor out the B prime C, I get 1 minus cos 2 theta equals n lambda. But B prime C is DHKL over sine theta. But there's a trigonometric function that says that cosine 1 minus cosine 2 theta is the same as 2 sine squared theta. So I can substitute this in here, and you'd have 2 sine squared theta divided by sine squared theta, so you end up with 2 DHKL sine theta equals n lambda. And that's what we call Bragg's law. I'll make one little addition here. Since this is a function of h, k, and l, and this is a function of which wavelength we use, then this means that the angle that we observe the constructive interference on will be a function of h, k, and l. In other words, for each h, k, and l, I'll calculate a d, use this equation to calculate the theta. If I measure intensity of light as a function of theta, in other words, if I scan these incoming rays through different theta, I'll see nothing, 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 and then all of a sudden I'll see constructive interference. And I'll continue scanning, I'll get another reflection. We call these reflections. This is called a diffraction pattern. And the position of the peaks is determined by the crystal structure.